So welcome back to our class. So we were discussing about ray optics. So we'll continue the topics about ray optics. So just as a fast recap, we can see from where we started. So we just started the ray optics, and in that one we discussed about the reflection of light by spherical mirrors, focal length, all those things we done, and total internal reflection, and we reached up to the optical fiber, and we were discussing about the optical fiber, the application of optical fiber. In that one we are using this optical fiber for communication, and this optical fiber is an application of total internal reflection. That's what we done last. And here we had a core and we have a cladding, so that it is undergoing total internal reflection. So because of the total internal reflection, even in a curved path we can move. So that things we discuss here. Now we will move to the next part. So here we are discussing about the refraction at spherical surface. That is, we have to go for the derivation of the refraction at spherical surface. That is, we are discussing about a lens, how the lens formula is coming. Before that one, instead of directly going to the lens, what we will do is we will first discuss about a spherical surface. That is, we have a curved spherical surface like this. So this one, let it be something like a liquid drop, or this is a ball made up of glass or something. Here we have a higher refractive index, and this side we have a lower refractive index. So that's given here. So we have this blue color, what you are seeing. This is of higher refractive index. Here we have lower refractive index. So in such a situation, how the light will travel or how the light will bend, that's what we will discuss first. So first we will go for this diagram. Once more, I will draw this diagram here so that you will understand how to draw the diagram. So here we have an object, and this is the principal axis or the axis which is passing through the center here. And from here, you see here, the light is going like this. And actually, this will be far away. For time being, we are drawing it like this. That's all. And here we have the normal. Normal means it will come to the center of curvature here. So as it's a spherical surface, the normal will come to the center of curvature. And now this ray of light, it will come like this, and the image is formed here, this point where we will write it as I. So the image is formed here. And now you can see this is the angle of incidence here. So the light is coming like this and it is falling here. That's what we discussed. Okay. So this is the point O where object is there. Here is the image. And the radius of curvature will be this one. This much will be the radius of curvature. And this is the angle of refraction here. And this point is M. And here this point is N. Now this will be the object distance U. And this will be the image distance V. Now we have to go for a connection between all these things. What is object distance? What is image distance? All those things. We have to go for a relation between all these things. Okay. So for that one, first we will take this here. So first you have to take the angle NOM. So which is NOM? This is N. This is O. This is M. This angle. Okay, that is in this diagram, this angle. Okay, both are same, only that to make it clear, I just drawn a little bit bigger, that's all. So here we have angle NOM. So this tan of angle NOM, you see here the tan of angle NOM is MN by OM. So MN is this one divided by OM. This will be the tan of that angle. So tan of angle is a MN by OM. So already you know tan theta is approximately equal to theta for small angle. So you can write this will be equal to NOM itself. Okay. And similarly, if you take angle NCM, NCM means this one. Tan of that angle will be MN by MC. That is MN, this one by MC, this one. This also will be approximately is equal to angle NCM itself. Similarly, we have tan of angle NIM. That is for this one, we will get it as MN by MI. So that is also approximately equal to angle NIM, like that, because of tan theta for small angle, tan theta is approximately equal to theta. So we can write like this. Now you see here, The next point is important. Now you see here, for the triangle NOC, that is triangle NOC, that is for this triangle NOC, this angle I is the exterior angle. This is exterior angle. So if you add these two, you should get this I. Okay, so what we can write? I is equal to NOM plus angle NCM. That is, this exterior angle should be equal to sum of these two. So we can write these two angles already we taken here. So what you will get? You will get I is equal to, angle I is equal to MN by OM plus MN by MC. That is, this exterior angle will be sum of these two angles. That's all. Similarly, we have to find out R. That is this R. This R will be, actually for this triangle, if you take this exterior angle should be sum of these two. So if you take like that, you will get R is equal to this angle NCM minus angle NIM. You'll get like this. So this angle R is equal to MN divided by MC minus MN divided by MI. Like this you will get. Just I want to tell you, we will get this angle R and I will get an equation, and for R we will get another equation. Now what we have to do is, we have to use our Snell's law. Sin I by sin R is equal to refractive index, or N1 sin I is equal to N2 sin R. That is just rearranging that one. Then you have to put the value of N1 and the here also you can see, for small angle sin theta is equal to theta. So what we can write? You can write N1 I is equal to N2 R, because here we have sin I and sin R. For small angles, instead of sin I and sin R, we can write I and R. Okay, so you will replace that value. So on replacing that value, you will get an equation like this. And in that equation, this what is there, OM, MI, all those things you can substitute using OM is equal to minus U, and MI is equal to plus V, MC is equal to plus R. All these values we have to substitute, so that we will get N2 by V minus N1 by U is equal to N2 minus N1 by R. So you'll get an equation like this. So this is important. Okay. Actually, nothing new in this one, just mathematical, just steps are there. So that's why no need of spending more time on that one. So you'll get like that. So this is the equation. Okay. No, not that one. We got this equation as the final equation. So this is the equation for our spherical surface. So here you see, this is applicable when you have one medium here, the denser medium, here one rarer medium. So the light is coming from here to here. You see here. So N2 by V minus N1 by U is equal to N2 minus N1 by R. So we have an equation like this. So see here, we are discussing about the refraction at a spherical surface. Actually, our full derivation when you are taking, we have to study about the refraction by a lens. So in order to study refraction by a lens, first you have to take refraction by a spherical surface, that is one surface. Now if you take the case of a lens, in the next one you can see that lens is actually two spherical surface. This side one spherical surface, another side another spherical surface. So this one you have to use there. So according to the question, sometimes you have to start from this equation. Sometimes you have to start from the beginning according to the question and how much marks question and what is asked, like that. Mostly they used to give this equation, and from this equation you have to find the lens maker's formula, like that. What is lens maker's formula? It is coming in the next part. Okay. So see. So now we'll go to the refraction by a spherical lens. Here what we are doing, you just listen. We have a lens like this. So for this lens, we have one side here. This side is a spherical lens, or a part of a sphere. And this side is another sphere. So these two spheres combined and this much area makes the lens. So in this derivation, what we will do is, you will take first one surface and you will see where the image is formed. then that image will be taken as the object for the next surface. Then we will calculate for the next surface. Now, after doing that for both first surface and second surface, you just add the equation. Then you will get for the total length. So that's how we will do. Just we'll see that one now. So we will first think about this surface. Okay, this surface you will see. So we have a surface like this. If you want, we will make it a little more bigger. Okay, I think this is visible now. So we have a surface like this, curved surface here, and we have the O here. Object is here, and the light is going like this, and it is going to this. This diagram is same as the previous diagram. The light is going and it's making a image I1 here. Why we are drawing I1 here means because when we are considering the next one also, the final I is coming. So due to the first surface, we have image I1 here. Now you see here, the previous equation, we had this equation. If you apply this equation for this surface, you will get N1 by OB plus N2 by BI is equal to N2 minus N1 by BC1. BC1 means this distance. Previously, that here instead of B, another letter was there. That's all. I don't remember that one. Another letter was there, but it's same only. So you'll get it like this. Now, same way, I am writing for this surface. When you do for this surface, the entire thing changes. We discussed previously the sign convention. When you take positive and negative, what we have to check, what is the direction of incident ray, all those things you discuss. Here, when you apply this one, you see here, the same format is there, N1, N2 is there, here where N2 is there, N1 comes, here N2 minus N1, here BC1 is there, here DC2 is there, here OB is there, but there is a minus sign here, there is a difference here. The reason for that one is, in the second case, what happens is, the image formed by the first one, I1, that is here, this line is same as this line. So this I1 is acting as the object in this case. Once more, let me explain that one. That's we have one surface here. I'll tell you like this. This surface makes the light to go here. So this is I1. When you take the next surface here, due to the next surface, again it is bending here and I is coming here. So for the second surface, what is the object? The image formed by the first surface becomes the object for the second surface, so that the final image is coming here. So now the object is that side. Generally, the object will be this side. When object is this side, incident ray is going that side. So we have a sign convention. But for this surface, the object goes that side. So the incident ray will be this side. So that's why we have a difference. So when you directly check the sign, there will be a difference this one. So you should know that difference came because the object is that side. So we have this equation. I think it is clear now. This equation is for this surface. And we have another equation, this one. This is for this surface. Now what we have to do? We have to combine this one. The first surface and second surface, we have to combine. So when you combine the first surface and second surface, what you have to do? Just you have to add that one, that's all. The first surface, you add this first and second surface together, then you will get it. But when you are adding, you see here, here we have something called as BI1 and DI1. That is, here we have BI1, here we have DI1. So you see here, what is BI1? BI1 means from here to here the distance. That is from this edge to here. This distance is BI1. And what is DI1? That is from this edge to here. That is distance from here to here. This is DI1. And as per our calculation, this image is formed far away. For example, it is 10 centimeter, 20 centimeter and on. And this lens is thin. In the lens formula also you might have heard thin lens formula. We will consider the lens as thin lens. So these 2 points can be taken as very close. So BI1 is equal to DI1. Why we are doing like this means, you see here we have N2 by BI1. Here you have N2 by DI1. If both are same, this will be N2 by DI1. Instead of that one, we can write N2 by BI1. Here it is plus, here it is minus. So that will cancel each other. So when you add these 2 equations, you will get a equation like this. that I will write a little bit bigger. Okay. N1 by OB plus N1 by di is equal to N2 minus N1 into 1 by BC1 plus 1 by DC2. Like this, you will get an equation. Okay. So you will get an equation like this here. Now, this equation to get, you have to add these two along with that one. You have to consider BI1 is equal to DI1. Then only you will get like this. Now you see here, this is a general equation when you have two surface. Now, this is OB means what is that? This is the object distance. This side, object distance. And what is this DI? That is the image distance. So we will go for a special condition. That is when the object is at infinity, where the image is formed. You know, when the object is at infinity, the image will be formed at focus. So if this is infinity, what will happen? This term will go. Then when this object is at infinity, image is at focus. So what we can write? N1 by F is equal to, the remaining is same only. N2 minus N1 into 1 by BC1 plus 1 by DC2. Same thing you can take. But here it will be N1 by F. Okay, now you got an equation like this. Now one more thing is there. This, what is this BC1? BC1 means from here to here. That is the center of curvature of this one. And here DC2 is the center of curvature of this. Actually, it's the radius of curvature of this one. Here, radius of curvature of that one. But here we have a plus sign. But in this case, one radius of curvature, that side is plus. This side it is minus. So what we can write? 1 by F. Actually, it is N1 by F only. We'll divide this entire thing by the N1 also. So it will become 1 by F is equal to, here I am dividing with the entire thing with the N1. So N2 by N1 is N21. Here also dividing with the N1. So it will become 1. Into this one, 1 by BC1, that is R1. Then plus is there, but we will have minus R2 toward this side. So it will become minus 1 by R2. So I will get an equation like this. This equation is very, very important. This equation is called as our Lensmaker's formula. This one is called as Lensmaker's formula. So we derived this Lensmaker's formula. So already you might have done in the class. That's why we done a little bit fast. So 1 by F is equal to N21 minus 1 into 1 by R1 minus 1 by R2. This equation is called as Lensmaker's formula. Why it is called as Lensmaker's formula? Because if you want to make a lens with a particular focal length, you want a lens which is of a focal length 13 centimeter. So if you want 13 centimeter focal length, you can use this equation. You know which material is used. It's refractive index minus 1. So how much is R1 and R2 required? What is the radius required? How much curvature is required? That you can calculate and you can make a lens. So that's why it's called as Lensmaker's formula. Now, this is the direct derivation. So this is the derivation itself can come. More than derivation, there are so many other things about this one. You can get questions based on this one. Direct substitution questions can come. And another type of questions, already we prepared that one to, after this one we'll do. That is, when you have a lens, when that lens is immersed in water, what will happen to the focal length? So when you immerse that lens in the water, what happens is, here this N21 is there, now that will change. Okay, so what happens is N21 will become that value, it will change. So this one remains same. So this one, when you divide that, you can cancel, and this only this ratio. We have a problem like that. There you will get the clear idea about that one. That is, when you immerse a lens in the water, or when you immerse lens in another liquid, what will be the focal length? That's a very, very common question. So we have to use this one. So it is not direct substitution. This N21 we have to change according to that one. So if R1 and R2 is given directly, you can do it. But in most of the cases, this R1 and R2 may not be given, because when you put inside the water or outside the water, this R1 and R2 remain same. So no need of giving that one. So first case you can write and divided by the second case. So when you are doing this R1 and R2, this part will get cancelled and the remaining you can rearrange to get the focal length. So such questions you will do at the end. So that's about the Lensmaker's formula. And one more thing, in this Lensmaker's formula, we have 1 by f here. See, this one is, see, this 1 by f is here. And here we have this equation also, by n1 by OB is u. And n2 by di, that is v. That if you substitute in this one, you will get the equation of that lens. Normal lens formula is then what is studied in 10th standard, 1 by v minus 1 by u is equal to 1 by f. That if you get this one and this one, you will get that one also. That I not prepared in slide, because directly you can do it. It's a simple thing. That's why that is not prepared. That is, you have to compare the LHS of this equation and this equation. So if you take that one, you will get the lens formula also. So lens formula and Lensmaker's formula is different. So this is Lensmaker's formula, and 1 by v minus 1 by u is equal to 1 by f. That is actually a thin lens formula or lens formula. Lensmaker's formula is this one. Okay. So here what you should remember is the focal length of this lens depends on the refractive index of the material, also the refractive index of the surrounding. So actually the difference between that this one, the ratio between the inside the material and the outside. And again, 1 by the radius, both side radius also is important. Okay, so this, and one more thing, if both side radius for numerical problem, children used to make a mistake. If both side is 20 centimeter, 1 by 20 minus 1 by 20, like that, it will become 0. Don't do like that. Both sides are 20 centimeter means this side will be plus 20 and this side will be minus 20. That you have to remember. Then only you will get the correct answer, because you have to take the sign convention. I already told you, even if you take the sign convention in the derivation, when you are doing the numerical, again you have to take the sign convention. So now you'll move to the next one. That is power of lens. So in 10th standard already you studied the quantity power of lens. What is power of lens? Power of lens, P is equal to 1. Here some problem is there. Power is equal to 1 by f. So how this power becomes 1 by f, that you have to check here. So power is equal to 1 by f. When you are doing calculation, you have to remember that one. This f is in meter. So that always you have to remember. When you calculate the power of a lens, power of lens is given by 1 by f, where f is in meters. If it is given in centimeter, you have to convert into meter and do. Otherwise, it will go wrong. And what is the SI unit of power of a lens? I think you know it is the diopter. We will denote it with a capital D. So diopter, 1 diopter means 1 by f. F will be in meter. So this 1 diopter means meter raised to minus 1. That's called as diopter. So generally we'll write it as D. So for your specs and all, you have power, positive power, plus 1, plus minus 1, or plus 0.5. So that is the power here. That is 1 by f. So that also you may as it is 1 by f, focal length is positive, means 1 by f also will be positive. So power is positive means it is a convex lens. If power is negative, then it will be a concave lens. So from directly from this one you can get it. Still questions can come based on that one. The power, when you are writing the final answer, the power you have to check whether it's positive, negative or not, because also negative means it's a concave lens, positive means it is a convex lens. And don't confuse this power with mirror. In the case of mirror, we are not doing, we are doing it for lens only. Okay, so in the case of mirror, such a concept we are not studying here about the power and all. We are doing it for lens. And one more thing you see here, this focal length, we have such a long equation for lens. In the case of mirror, such things are not there, just R by 2, because it is independent of the refractive index of the material or refractive index of the surrounding medium. Got it? So I have told you, when you put a lens in the water, what happens? Like that question will come. But if you put a mirror in the water, nothing will happen. So if you use a mirror inside water or outside, everywhere the focal length will be same. Similarly, even when you are changing the color, if you have a blue light and red light, then in the case of lens, the focal length will be a little bit different. In the next topic, we'll study how it is becoming different. But in the case of mirror, that will not come. In the case of mirror, whatever be the color you are using, also the focal length will be same. Okay, now we'll come back to this one. So the power of the lens is P is equal to 1 by f. So how we are getting that power of lens as 1 by f? So as per the definition of the power of lens, it is the tangent of the angle by which a light ray bends when the light ray is falling at a unit distance from the center. Okay, so when it is given as a sentence, it is little bit difficult, so I will explain it here. That is, you have a lens like this. What it is saying is, once if a ray of light is falling here like this, parallel to the principal axis, at a distance, unit distance means 1 meter away. That is, from the center, 1 meter. Our lens is not 1 meter and all, but the definition is like that. Okay, at 1 meter away or unit distance away, if a ray is falling, it will come like this. So it will make an angle here, delta. Tan of this angle delta, if this is delta, this also will be delta. Tan of this delta, that is called as power of lens. So power of lens is tan delta is power of lens. So this is 1 meter, this is h. So what is tan delta? Tan delta is h by f. So already we have h is equal to 1 meter or unit distance. So tan delta is equal to 1 by f, because if when it is coming parallel, it will go and meet at focal length f only. So tan delta is 1 by f. So we can write power is equal to 1 by f. This is how we are getting power of a lens as 1 by f. Okay, and the SI unit of power of lens is 1 diopter, that we already discussed. Okay, and if the power of lens is negative, it is a concave lens, and if power of lens is positive, then it is a convex lens. So I think that part is clear. When the power of lens, how to calculate and all. And one more thing, this power of lens, when we are discussing how to keep the lens in contact. When you keep many lenses in contact, that is coming in the next topic. There we will discuss. Okay, when you are keeping in contact, what will happen to the power of lens and what will happen to the focus and all. Okay, anyway, it is there in the next topic, so we will see there. So see here. Here we have combination of thin lens. So first thing what I have to tell you is, this is applicable when this lens is very thin and they are in contact. You have one lens here and it's very thin, and another lens which is very thin, both are kept in contact. So what will be the total focal length? It doesn't mean that both should be convex. It can be convex and concave, or both can be concave, or both can be convex. The lens should be thin, that's all. So when two lenses are kept in contact, what is the focal length? That's what we have to do now. So we'll check it. So here you see we have one lens. First you think about one lens only. So our object is here. So from the object the light is going like this. So that makes an image here. This image is I1, and this U is the object distance from here. Okay, and this will be V1. Now you see here, when we keep the second one will again bend the light little more. So this is the final image. I think you got the idea. That is, the light is going like this, and this makes the first image when only one lens is there. When we have the second lens also, it again bends little more, and here comes the image. So this is the final image. Actually, such an image is not there. But here we have to do according to the previous situation, how we discussed. We have the first lens that makes an image here. And for the second lens, when we do for the second lens, which is the object, this is not the object for the second lens. For the second lens, object is the image made by the first lens should be taken as object for the second lens. So I will do like that. First we will think about, so here A and B, two lens is there. This is A and this is B. So for lens A, we will do first. For lens A, what is the equation? The 1 by V minus 1 by U is equal to 1 by F. So 1 by, for the first one, that is V1 minus 1 by U is equal to 1 by F1, where F1 is the focal length of the first lens. Now for the second one, when I am writing, should be very much careful. What is the object distance for this one? That is the image made by the first one. And the image distance is this V, the final image. So we can write 1 by V, where V is the final image, that distance. 1 by V minus 1 by U should be there. U is the object distance. For the second lens, the object is the image made by the first one. So this will be V1. 1 by V1 is equal to 1 by F2. So we got two equations here. Now when the combination comes, you have to add this one. You can clearly see here 1 by V1 is there, here minus 1 by V1 there is there. So that will get cancelled. So what you will get, 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. So you'll get an equation like this. 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. Now you listen here. If in case this was a single lens, that is, this is not lens, you consider it as a single lens, the total. Then what should be the equation for that one? 1 by V minus 1 by U is equal to 1 by F. What is this F? This F is the focal length of the combination. Now you compare these two equations. When you compare these two equations, what you will get? 1 by F is equal to 1 by F1 plus 1 by F2. So that's it. So when you have two lenses in contact, the total focal length you will get like this: 1 by F is equal to 1 by F1 plus 1 by F2. So if this one lens becomes concave lens and another is convex, means this F will become plus or minus according to that one. That's all. Okay, so that's a very simple thing. Now, when these two are convex lens, what happened to the focal lengths once you see that one and see? When you have two lenses like this, they are kept in contact, whether the focal length will increase or decrease. It is 1 by, just like our resistance when it is connected in parallel. You have 10 ohm, 10 ohm. When you connect 10 ohm and 10 ohm in parallel, it becomes 5 ohm. So similarly here, you have two lenses. So when you keep these two lenses in contact, what will happen to the focal length? The total focal length reduces. So when total focal length reduces, what will happen to the power? The power increases. So actually 1 by F is power only. The total power of this one, how we can write? Power is equal to, the total power is equal to, oh, another thing on. Okay, so the total power is equal to, P is equal to P1 plus P2. That is, our equation was 1 by F is equal to 1 by F1 plus 1 by F2. So the power is equal to P1 plus P2. Like, oh, sorry, this is next page. Okay. So this is P is equal to P1 plus P2, like this you will get. Okay, P is equal to P1 plus P2, like that you will get. Okay. I think this is clear. So the power increases. Now, this one we have different types of application. And what about the magnification? Magnification, you know, the size of the image divided by size of the object. So the focal length will be adding like this: 1 by F is equal to 1 by F1 plus 1 by F2, like that. The power will be adding like this. Magnification will get multiplied. The total magnification M will be M1 into M2 into, if you have more, M3, like that you will get. So for this one, we have some more application. So we'll go for that one. That is, you think about a question like this. You have a lens like this. Both sides are same. Now, if you are cutting this lens into two parts like this, so this becomes one lens and this becomes one lens. What will happen to the focal length? Whether it will increase or decrease? So you see here, it became two lenses. One lens is here, another lens is here. It became two parts. Now, what will happen to the focal length? How we can get it? So when I ask like this, it will be a little bit confusing for you. You think in the opposite way. Previously, you had one focal length F1 here. We had another focal length F2 here. When you combine this one, what will happen? The focal length it will become 1 by f1 plus 1 by f2. So the focal length reduces. So when you split it like this, the focal length increases. That's all. In the same format, you have to take in the opposite way. This is 1 by f1, this is 1 by f2. So I see this is applicable when you cut straight only. Okay, if you cut inside something, it will become different. Okay, so if you cut straight, you will get f1 by f2. You can get like this. Okay, so it's very important. If you cut a lens like this, the focal length increases in such a way that 1 by f1 plus 1 by f2 is 1 by f. Okay, now anyway, we discussed about cutting like this. One more we will discuss in the same point. Later, we may not get time for that. You have a lens like this. If you cut this one, this portion is broken and it's gone. Only this much is there. Then what will happen to the focal length? You have a lens like this and only this part is there. What will happen to the focal length? The answer is nothing will happen to the focal length. The focal length will remain same. And one more, you think about the image formation also. What will happen to the image? That's also a valid question. You have a object kept here. The image is formed here. And the lens is kept like this. The half of the lens is broken or you paint it with black. Both sides you are painting it with black. So that what will happen to the image? You have a big lens and half of the lens you are painting with black. What will happen to the image? You see here, its answer is simple. The light comes like this and it will come. All those things will be same only. But the thing is here, this light will not come. This area light will come. It doesn't mean that if this area light is coming, it's one part of the image which is not seen. It's not like that. Because from each point, all the way the light will come here. So all the parts will be visible. So focal length will not have any difference. And the size of the image also will not have any difference. Same focal length will be there, same magnification will be there, position of the image will be same, everything will be same. Only thing is some light will not reach there. That's why the brightness of the image will be a little bit less. So many times that question came, it can come again also. If you take the case of a mirror, or concave or convex mirror, or if you take the case of a lens, concave or convex, this half of the part is broken or the half of the part is covered, then the image will not have any difference. That is, the brightness only will change. The brightness of that image, the size of the image will be same, and the position of the image will be same, and magnification will be same, everything will be same. Only difference what is possible is its brightness will be a little bit less. Okay, if you cover this little bit part of this one. That's what you can see in the case of telescope. We are studying it like that. In the telescope, in the center of that one, a mirror comes, it blocks something. So when you look through the this eyepiece, you are not seeing a black area or something. Once some area is closed, means that much light will not come. That's all. Especially when you are looking at a sun through a telescope, that big round opening is there, means they will cover that one as a 1 centimeter, 2 centimeter hole only they will keep, so that very less amount of light will come inside. So if the less amount, if the aperture or the opening is very big, means more brightness will be there. That's all. In the case of sun, we don't want that much brightness. That's why they used to close the telescope. Only a small opening they will keep. Same way here, if one part is closed, it won't make any difference. Only the brightness will be different. Okay, so I think that's over here. And dipping in the water and all we will discuss later. Now refraction through prism. So now the step-by-step derivation, I think it will waste time only. We have a prism like this, and the light is passing like this here, and it is coming out here like this. So you know, when the light is passing through a prism, it will deviate towards the base. It will deviate toward this side. So why this is bending? Actually after the derivation only that the exact answer will come. Still anyway we study in 10th standard also. That's why we can say if it is a colored light, it will split into different colors. So this because of the refractive index, it is bending. Okay, the light is bending because of the refractive index. Inside and outside the speed is different. So light will go in a path in such a way that it can reach with the shortest time. So from here to here, if the light is going straight, it should pass more distance through this glass. So it will take more time. So if it goes like this, it should travel more distance. So that also will take time. So this is the easiest path. Easiest path means it will take the shortest time in this way. So that it will go through that path. Okay, so it will bend like that. Now, you see here, when the light is falling like this is supposed to go straight like this, but it is bending from here and again it's bending like this and it's going like this. Now you see here, for this derivation, you have to take this quadrilateral like this. So in this quadrilateral, you can see angle A plus angle QNR. That is, this angle plus this angle will be 180. And again, see here, this angle plus this angle, R1 plus R2 plus QNR, this one. That is, this triangle, if you take, total will be 180. So if you compare that to, you will get R1 plus R2 is equal to A. That's a thing. That is, you will first take this one, this quadrilateral. So this is 90 degree, this is 90 degree. So remaining these two, if you add, it should be 180. Similarly, for this triangle, all the three triangles, if you add, it should be 180. So if you compare that one, you will get R1 plus R2 should be equal to A. Now you see here we have deviation. This is very important. This is called as the total deviation. This total deviation should be sum of, see here, this total deviation, this should be this angle plus this angle. Here one angle is there and this one angle. What is this angle? If you take like this angle and this total should be same. Now, this small one means total from this one, you have to subtract this one. So that is, we can write delta is equal to I minus R1. And in the other side also, if you take like that, plus E minus R2. Okay. E minus R2. We are moving a little bit fast because this is just derivation part. Okay. Now you will get the, finally you will get delta is equal to I plus E minus A. Like that you will get the deviation here. Okay. Now we'll move to the next slide. So here you can see the remaining part of that one. That equations, just you will forget that, the physical concept you will take. Okay. So what happens is, when the light is passing through the prism like this, it is undergoing a deviation. Now, if you change the angle of incidence, the deviation also will change. That's very, very important. So you see here, this is a graph which shows that for different angle of incidence, this is angle of incidence here, this is angle of deviation. If you change the angle of incidence, you will get different angle of deviation you will get. So you can see here, the angle of incidence, when increases, the angle of deviation first reduces. This is required for your practical also. So you can see here, the points you will get like this. Okay. So what's here? The angle of incidence, when increases, the angle of deviation reduces, and then it increases. So there is a particular condition where the angle of incidence is minimum. Sorry, angle of deviation is minimum. That is called as DM, minimum deviation, angle of minimum deviation. When this angle of this will be minimum, the deviation will be minimum. That is when I is equal to E. That is here this I and E is there. When this I and E are equal, we have the minimum deviation. When this I and E will be equal, simply we can say when this ray passing inside this prism is parallel to the base. If it is a exactly triangular prism, when this is parallel to the base, this I and E will be equal. Okay. Now you see here, we have when I is equal to E, when you substitute that one in the previous equation, you will get 2R is equal to A, or R is equal to A by 2. Now see here, for I also we have a equation, and for A also we have a equation. I equation in the previous page, it's gone. Now what is that? Refractive index is equal to sin I by sin R. Refractive index is equal to sin I by, the refractive index is equal to sin I by. So I was A plus dm by 2, and R was sin A by 2. Okay, so you will get the thing, and I know the step something is missing in that one. That's in the previous page actually. Okay, so just you should know this is the equation for refractive index. then when light is passing through that one, it bends. Now you see here, this deviation, how much it is bending, that depends on the refractive index, or the refractive index depends on this bending. So different colors is bending different way. When the light is passing through the prism, what happens? Different color is bending in different ways. So the meaning is different color is having different refractive index. The violet is having the highest refractive index. That's why it will bend the most. And the red is having less refractive index. That's why it will bend less. Okay. So this bending effect is only makes the lens to focus. So there also, according to the color, some difference is there. All the colors are not bending equally. Some colors are bending more and some colors are bending less. In the case of lens also, that makes a problem in the lens. That is called as chromatic aberration. When you study about the telescope, as a defect of telescope, we are using the thing called chromatic aberration. So this chromatic aberration means the different color will bend a different way. So all the color will not focus to the same point. So there will be some distraction in the image. That is called as chromatic aberration. So that is happening because of this one. Because this lens can be considered as made up of small prism. So each one is a prism. So when it is bending, this light will focus to different points. So that's why small difference will be there. Actually, the difference in the refractive index is very small. That's why a minute difference will be there. But when we are magnifying using glass and all, it is a problem in the case of telescope. That's why that we'll discuss later when we go to the telescope part. So I think this is okay now. Now, we will move to the optical instruments. In this optical instruments, first we will discuss about microscope. So in microscope, first we will discuss about a simple microscope. Simple microscope means just one small lens only. Okay, simple lens is there. So we have to find out what is the magnification of this one. So here, if see this microscope, we have two types of adjustment. That is the microscope. If it is a single lens, if it is a simple microscope or in compound microscope, we have two types of adjustment. So one adjustment is in such a way that the image is formed at D. What is this D? Least distance of distinct vision. That is called as D. When the image is formed at D or the near point, 25 centimeter. So we have one adjustment. That is called as a near point adjustment. And here we have another adjustment where the image is formed at infinity. So that is called as the normal adjustment. So we have two types of adjustment. So the magnification is different in both cases. So we will see what is the magnification in both cases. First, we will see about this picture where the image is formed at D. So we know the magnification M is given by V by U. V by U means it is actually V into 1 by U. So you can write magnification as M is equal to V into 1 by U. That is equal to 1 by V minus 1 by F. This V can go inside. So it will become 1. That is V by V will be 1. And this will be V by F. So magnification can be written as 1 minus V by F. Okay, 1 minus V by F you can. Now you see here, what is this V? V is the image distance. So the image is formed here at a distance D. So V will be this minus D. So now your magnification will become M is equal to 1. Instead of minus, it will become plus because V is equal to minus D. 1 plus D by F. So this is the magnification. When the image is formed at the distance D, the magnification is given by M is equal to 1 plus D by F. The magnification is equal to 1 plus D by F. You will get like this. So once more, we will discuss how it is. If it is not clear, the magnification is given by V by U. Now in this one, you see here, the U is this one and V is D or the near point. So here we have magnification is equal to 1 by, V by U or V into 1 by U. What is 1 by U? 1 by U is 1 by V minus 1 by F. So magnification is equal to M into 1 by V minus 1 by F. So this one can be written as 1 minus V by F. And this V means this is V, but it is toward this side where the object is there, so it can be written as minus D. So if instead of V, if you put minus D, the magnification M will become 1 plus D by F. So when the image is formed at D, the magnification is given by 1 plus D by F. Now we'll go for the magnification when the image is formed at infinity. That is this one. When the image is formed at infinity, the importance is when the image is formed at infinity, we cannot get the value of V and V because it's at infinity. So the magnification cannot be infinity also. So what we have to do is when the image is formed at infinity, instead of taking this linear magnification, we will take angular magnification. So what is angular magnification? Angle made by the image divided by angle made by the object. So here you see the object is kept here and the same line the image is also made. So there also we cannot take this angle made by the object here. This is the angle made by the image. So what is angle made by the object? So angle made by the object means when the object is kept at D, that is without any lens, when you are keeping at your comfortable distance, that is at this point D, at 25 centimeter away from your eye, what is the size of the object? That is that you have to take, and you have to take the angle made by that object. So this diagram gives that one. Once more, I will tell you. When you take the angular magnification, it is the angle made by image divided by angle made by the object when it is kept at 25 centimeter. Not at this position. When it is kept at 25 centimeter, what is the angle made? That's what you have to take. So the height of the object is H, and this angle is the angle made by the object. So this is D. So what will be the value of theta made by object? Theta O. Theta O will be equal to H by D. And here you see the image is formed at infinity. So here the value is theta I. Theta I is equal to H by, see here, when the object is, the image is formed at infinity, the object will be kept as F. H by F. See here so much other stuff is there. I am going it direct. Okay. So theta O is this one, theta I is this one. Then what is our magnification? Magnification is this one. Magnification M is equal to theta I by theta O. So magnification will be equal to just D by F. Okay. So we have two magnification. When the object is kept at infinity, when the image is formed at infinity, the magnification is D by F. And when the image is formed at D, the magnification is 1 plus D by F. So it is very clear that the magnification when the object is, when the image is formed at D, that is more. If this is 20, that will be 1 plus 20. So it will be 21. One you will get extra. But here one very important point is there. Even though the magnification is more in this case, we will prefer this one. So for that one, what is the reason? Okay, I told that the entire derivation to tell that point. Okay, because derivation you already know. So here, the magnification of this simple microscope is more in the case of this image formed at D, but still we will use this one because when we see the object, we are looking inside the microscope. So our eye, we have to concentrate on the image for more time. So you know, when you are looking at an object which is very close to you, and when you are looking at an object which is far away, that is different. So you know that our eye, the ciliary muscles and all is studied in 10th standard. So when eye is relaxed, it will be focusing at a long distance. That's why you will feel very much relaxed when you are seeing an object which is far away. You have open space, you will feel it as relaxed. And when you are reading something, you will get a strain after some time. So in this case, what happens? Your eye will be relaxed. So even though the magnification is little bit less, we will prefer this one because the eye is relaxed. And this one we will prefer because we will not prefer because we will have strain on that one, even though the magnification is more. Okay, so we'll go to the next one now. Next one is compound microscope. So in this compound microscope, the first thing is you should know to draw this compound microscope. So sometimes even the last examination also, I think you got a question to draw a microscope or telescope. So we have three diagrams. One is for compound microscope, another one is for this refracting telescope, another is for reflecting telescope. So you should know how to draw this one. Okay. So the first thing is generally what you will do is you will draw this lens first, then this lens, and you will draw like this. So it will not come to this one. So the easiest way to draw is you draw the lens, this lens first, then you draw like this. You draw the object here, you make a small object, don't make it very tall. Okay, because when it goes tall, this line will come down. You have to draw a very big lens, then only it will reach to that. So you draw a small object here, and the light ray goes like this, and another light ray goes like this. You see here, after this crossing, there you draw the eyepiece. Then your diagram will be okay. Otherwise, if you draw this first lens here, second lens here, when you draw this one, it will not come to this one. It will make go down like this. It will be simply waste of time during the examination. That's why this one you draw later. First you draw across this one and draw. I am telling this one because we are seeing that one in most of the examination paper. They will draw it and it will not reach there. They will erase it. It is too much time waste will be there. So you do it like that. So you have a objective here and a eyepiece here, and the object is kept here. We are looking from here. This adjustment, you can see that the image is formed at D. So here we have to calculate the magnification. The derivation is simple here, okay? Because first we have to calculate what is the this one magnification made by the objective. So for that one, you see here you can take two triangles. This is one triangle, and here we have another triangle. So this is beta. This is also beta. Now you see here, what is tan beta from one triangle? If you take, you will get tan beta is equal to h by FO. And from the other triangle, you will get it is h dash by L. So what is this L here? L is not marked here. So that is very important. So you have one lens here, another lens here. So this is the objective here. This is eyepiece. This objective's focal point is this one, and eyepiece focal point is here. And the gap between these two, this is L here. Why I am stressing on this one means, in the case of a microscope, the length of the tube L is from the focus of objective to the focus of eyepiece. Okay. In the case of telescope, it is not like that. Telescope, the first lens to the second lens, the total length is called as the length of the tube. In the case of microscope, the L or the length of the tube is from this focus to this focus. You should remember that one because some calculation and all is there, because like this, here one crossing, here one crossing, two crossing is not there in the case of telescope. We'll see. See, the telescope here, one crossing only is there. So the length of the tube in the case of telescope is from here to here. But in the case of microscope, you can see here one crossing is there, here one crossing is there. So that is, this distance is L, length of the tube. Okay, so this is L. So you will get tan beta is equal to h by FO, which is equal to h dash by L here. So you are getting like this. So now if you rearrange this one, h dash by h, which is magnification, h dash by h is equal to L by FO. Just the point is, this one produces a magnification of L by FO. And what about the magnification of this one? When the image is formed at D, the magnification of this one is 1 plus D by FE. Now, what is the total magnification when you have two lenses? You have to multiply that one. So, the total magnification is given by M is equal to L into, sorry, L by FO into 1 plus D by FE, or magnification is equal to L by FO into D by FE. Why we written 2 like this? Because the situation is different. When the image is formed at infinity, this will be the magnification. When the image is formed at near point D, this will be the magnification. Here also we have two values for the magnification. It can be like this or it can be like this, depending on the position of the image. Still, you should remember this one more thing. This is magnification will be more, this magnification will be less. Still, we will prefer this one. The reason is the same thing only. We can watch it with a relaxed eye. Okay. So here, one more thing. Here both, if you want to get more focal length, more magnification, both should have smaller focal length, because such questions are coming later. That is, if you have two lenses, actually not two lenses, more than two lenses are there. So which one you will select for making a telescope? Which one you will select for making a microscope? Like that question will come. So you should see here, for getting big magnification for a microscope, both should have lower focal length. Okay, the focal length should be small for both. One more thing is that both should be small, and this should be again small. Comparatively, this objective should be again small. That we'll discuss later. So both should be small, and this one should be comparatively again small. And you see here, this size is very small. So when that question comes, you will understand that one. Okay. So anyway, this one you should know, the derivation and this diagram you should know. Okay, that's about microscope. So the microscope, once more, the final result I will tell you, that is, in the case of simple microscope, we have two magnification. One is, here it is, magnification is 1 plus d by f, and we have here magnification is d by f. And when you take, in the case of compound microscope also, we have two values here, and which one is preferred and why, that's also discussed. Now we'll move to the telescope. See here, when you take the microscope and telescope, first you should know what is the purpose of this one. Microscope is used to see some object which is very small, which is very close to us. We have to see that one. So it should have very high magnification, so that to see that one. And in the case of telescope, the purpose is different. Telescope is used to see an object which is far away, and we have to see that one. And the main thing is, the purpose of the telescope is not to show it as very big or something. The purpose of the telescope is to show very close points separately. So that is called as the resolving power of telescope. Microscope also is having a resolving power, but when you take the priority, in the case of microscope, our more priority is to magnify and show. But in the case of telescope, more than magnification, we will give priority to the resolving power. So what is the resolving power means? Resolving power is the ability of a telescope to show two nearby points separately. So if you have two stars very close, and if you are showing it as very big, and the image of the first one is spreading and second one is spreading, if it is mixing together, it is of no use. So if you are taking the normal telescope and see also, if you see the moon through a telescope, it is not magnifying and showing the moon as very big or something. It will show detail. In detail, it will show. So the purpose of the telescope is to get a high resolution image, not to get a very high magnified image. Okay, that's the first point. Now, when this diagram is drawing, the most of the children, what mistake they are doing is, they will draw an object here, just like the microscope. That is wrong. Actually, here the object is at infinity, far away. So the parallel rays are coming here, and it's coming here, and you are getting a image here. You see the lens also, the objective is very big and the eyepiece is small. Okay, and see here, actually when the actual derivation comes here, one more ray is there like this. Okay, one more, the textbook or 2 only is there. If you draw 3, you will understand. This is beta, here also it is beta. One more ray if you draw. Now what is magnification here? Here it's very important. Here we will take the angular magnification. In the case of telescope, you will take the angular magnification. So the angular magnification M is given by angle made by the image divided by angle made by the object. Angle made by the image is this beta. So it is beta divided by alpha. So here if you take the triangle, you will get alpha is equal to H by alpha is equal to H by Fe. Sorry, H by Fo. And beta is equal to H by Fe. So if you do that one together, the magnification is equal to beta by alpha, which is h by fe into fo by h. Or simply we can write it will be fo by fe. Okay. So the magnification is given by fo by fe. So here you can see, to get a high magnification in the case of telescope, the objective should have a larger focal length and the eyepiece should have a smaller focal length. So it is not like a microscope. In the case of microscope, both should have low focal length. Here the focal length of the objective should be large and focal length of the eyepiece should be small. Okay. Now, another point is there. I will explain along with this one itself, so that otherwise you will forget that. This objective will be having a large size. So always the quality of a telescope is explained based on the objective. So in this place we have a telescope of 1 meter objective, or this much inch objective, like that. So what is the importance of this large objective? So when we have large objective, we have two advantages. This is very, very important question. Why the telescope should have a large objective? So the first point is, when the objective is large, the amount of light entering inside, or the light gathering ability, will be very high. So the first point is, for the telescope, it should have a large objective because it should gather more light. Second one is, I told about the resolving power. That is the ability of the telescope to show two nearby points separately or distinctly. That is called as resolving power. So resolving power of the telescope will be very high when you increase the size. So because of these two reasons, the objective should be very large. Okay, so that's one important point. Now, we have this type of telescope. This is called as a refracting telescope because the light is refracting through this one. So this is called as the refracting telescope. And the other type of telescope, that is called as the reflecting telescope. This is also called as the Cassegrain type, because reflecting type telescope, we have Newtonian type, like that. Different type is there. What is there in your textbook, or what is there for you to study, is Cassegrain type. Very simple. From the diagram we can see here, it is a this is a reflecting type telescope. So in the reflecting type telescope, we have mirror. So see here, this is the main mirror. This is the objective mirror. So the light from outside, it is coming like this, and it is reflected here, and it is going like this. Here we have a eyepiece. So we have a secondary mirror here. This is called a secondary mirror. So in all the setup, this is not secondary mirror. Sometimes here a observer cage will be there, or some camera will be there inside. So this type is called as Cassegrain. So you don't feel this one as two pieces. Here one piece of mirror, here one piece. It's not like that. It's a full circle, and center we have a hole like this. When you cut from this and look from here, you are getting this piece and this piece. Okay, this is not two pieces like this, full circle with a hole in the center. Okay, and this is a reflecting mirror here, and you can look from there. Actually, this is more preferred comparing with the previous type. Simplest reason is, see here, previous you had one lens here, another lens here, and this should be kept at the focal length also. If you want to get a good telescope, the objective should have big focal length, we told. So this one should be too much behind according to the focal length of that one. Here nothing is there like that. If whatever length is there, that's enough. No need of making it very long. Okay, and actually that is an important question itself. Actually, what are the advantage of reflecting telescope? So we'll go one by one point. The first advantage of reflecting telescope is, if you take the refracting telescope, we have a lens. The lens is very much heavy because this is thick like this, very much heavy comparing with a mirror. Okay, and this heavy mirror, heavy lens, we have to support on the edges. We cannot support the back side because entire area light should come. But this one can be supported using the entire back side. So first one is, this is heavy. Second one, it should be supported on the edges. We cannot support that one. So here we can support using this one. And one more thing, we discussed about the chromatic aberration. When the light is coming like this, different color will focus to different point. That is chromatic aberration. So in the lens, we will have chromatic aberration. Here will not this one will not have chromatic aberration. And one more thing I told about the length. For this one, it should have more length according to the focal length. Here, such issue is not there. The length can be short. Okay, so that is one advantage. Like that, we have different advantage. So anyway, 3-4 advantage you learn about that one. And we have a limitation for this one. The limitation of this one is very simple. From the picture itself, we can see. Here we have a mirror or a observer cage, I told. The secondary mirror or the observer cage, that will block a part of light. The secondary mirror or the observer cage will block a part of light here. That is a big disadvantage. So its disadvantage is an advantage for the other one. And all other advantage of this one will be the disadvantage of the other one. So in this one, what are the things you have to study about telescope? Means diagram of both telescope you should know. And after that, the derivation for both the magnification of the first one. Here we are not discussing about the magnification of that one. And what is the advantage of this one and what is the limitation you should know. And why we need a large objective about the resolving power. That point you should know. And afterwards, that lens when you are taking for microscope and telescope, which type lens we have to use. The objective should be large. And for the case of microscope, both should have less focal length. In the case of telescope, the objective should have a larger focal length. All those points you have to study. Okay, so I think this topic is over now. Now we will go for some questions from this chapter. Okay, actually this chapter contains so much questions, we won't get that much time. So how much time is there, that much you will do. Because of the shortage of the time, we will not go for the numerical calculation of that one. We will just go for the concept, what is there in each question. Okay. So here you see an object AB is kept from in front of a concave mirror as shown in the figure. Like this one figure is there. Complete the ray diagram as showing the image formation of the image. That is just a 10th standard question only. You can complete it. Okay. Because this is beyond C. So where the image will come between this one. So you just draw this one, it will pass to the focus. This will go here, you will get it here. That's all. Okay. Then the next one is, how will the position and the intensity of the image be affected if the lower half of the mirror reflecting surface is painted black? If this area is painted black, how it will affect? Just now we discussed that one. In the case of lens, if you paint half of the part, then what will happen? Only the intensity will change. Okay, don't write it as half of the image will be going or something, nothing like that. Only the intensity of the image will be changing, that's all. Okay, so that question is very simple. Now the second question. Plane and convex mirrors are known to produce a virtual images of an object. Draw a ray diagram to show how, in the case of a convex mirror, virtual object can produce a real image. Okay. Then why are the convex mirrors are used as side view mirrors? This is 10. Second part is 10 standard. Why convex mirror is used as side view mirror means we have two reasons for that one. Second part we'll discuss first. Okay. So what are the first reason? It will show a large field of view. Second one is it always gives the erect image. Okay, it always gives the erect image, and second one is it is having larger field of. Now we'll go for the first part. A plane mirror or the convex mirror. Okay, we'll think about plane mirror first. You have a plane mirror like this. So you see here, when the object is here, the light is going like this. And when you see from here, inside here, one virtual image will be there. So when you will get a virtual image for a plane mirror, in most of the cases, when the object is real here, if the object is virtual, then you will get a real image. So what is the meaning of object is virtual? See here, you have a lens here, and the light is coming from here like this. So what will happen? These two will come and focus. I will draw half of the part. It will focus to this point here. Okay. Now, if I keep a mirror here, I am keeping a mirror here. So this is coming here. This is coming a little bit here. Okay. So actually, this two light is supposed to come here and meet here. If this is removed, it will meet here. But when you keep there, this is not meeting here, but it is supposed to meet there. So this is acting like a virtual object for this one. That is, if you keep a mirror there, actually, if that mirror is removed, the image will be formed there. When you keep the mirror there, that image which is supposed to form there, that will become a virtual object. So what will happen? This will reflect back here. And here we will get a real image. So a plane mirror shows a real image here. I think you got the idea. So for this real image, what is the actual object? Here we have a virtual object. So when the object is virtual, the image will be here real image. So you should remember that one. In the case of a convex mirror, also same thing. If it is convex, also same thing. For a plane mirror or convex mirror, when the object is virtual, you will get a real image. That's what they are asking how to. That one you have to explain by drawing the picture like this. Okay. So if this part is not there, also no problem. A converging ray comes means okay. You can draw like that. You have a like this, and a converging ray is coming like this. It is supposed to make the image here, but it will reflect back and the image is formed here. So that's the answer for that part. Okay. Now we'll go for another question. How is the focal length of a spherical mirror affected when the wavelength of the light used is increased? How the focal length of a spherical mirror, for mirror, no effect. Okay, for lens only effect is there. Okay. Second part, a convex lens has 20 centimeter focal length in air. What is the focal length in water? That is important. Okay. A convex lens has 20 centimeter focal length in air. So this is lens. Okay. As it is lens, it will change. So what you have to do? That equation was then a lens maker's formula. You have to write lens maker's formula once for what? Air. Then you have to write once more lens maker's formula in water. So what is the difference here? N21 minus 1 will come in that equation. When you are writing the second one, it will be N21 is there. So that one divided by the refractive index of water 1.33 will come there. And the remaining everything will be same. So this whatever is coming in the bracket, it will get cancelled. Here 1 by F1 will be there. Here 1 by F2 will be there. We will see the solution. It will be. So you see here the same thing. Here Ng minus 1 is there. Here Ng, here refractive index of water you have to take. And the remaining part will be there. So this one cross multiplied and you will get like this. Okay. So this is the way. Okay. This one, they are not shown the step before that one. So you will get it like this. Or you just remember this one, CC. Or you write two equations and you divide. Then you will get it like this. So here you are getting 80 centimeter. So the thing is, when you put a lens inside water, the focal length increases. That you should remember. Okay. If it is concave or convex, in both cases, it will increase. Okay. I will explain that one also for you. That is, see here, if you have a liquid like this and you are putting a lens inside this one, then what will happen? So if this is of a refractive index 1.5, you are putting in a liquid of 1.3. That is, if you put a lens inside a liquid with a refractive index less than that of the liquid, sorry, the lens, then what will happen? The focal length will increase. Concave and convex both. Remember clearly, you have a lens, you are putting inside a liquid which is having refractive index less than that of lens. Lens is made up of glass 1.5. The liquid is water 1.3. Then the focal length will increase. You see in here from 20 centimeter it became 80 centimeter. Now the next case is if the focal length, if the lens and the liquid is having same refractive index, then what will happen? That is a lens made up of material of refractive index 1.5. You are putting in a liquid which is having the same refractive index. Then what will happen? That is a very interesting thing. See here, this lens is visible here because this is having different refractive index. If this is what, if this is 1.5 and this is also 1.5, then this lens will become invisible, or it will act like a glass slab. Very, very important. When a lens is immersed in a liquid where the refractive index of the liquid and lens is same, then the lens will become invisible there. Okay, so that also is important. Now that's not over. It can be opposite also. That is, you have a lens. This lens is of 1.5 and the liquid is of 1.6. Then what will happen? If the refractive index of the liquid is more, then everything becomes opposite. That is, a concave or convex lens will behave like a concave lens. That is, when the lens is kept outside like this is converging like this. But inside this one, it will behave like a diverging lens. Very, very important. If you take a converging lens and put in a liquid which is having refractive index more than that of the lens, then the converging lens will become diverging lens. And diverging lens will become converging lens. I think you got the idea. So based on that one more question I will tell you. You think about a water tank like this. In this water tank, we have a bubble. A bubble. So inside this one, air is there. And here we have water. So the light is coming like this. So this will act like a lens. Which type of lens it will be, whether it will be concave lens or convex lens. From the shape, you will feel it as it is a convex lens, so that it will come like this. No, it will not happen like that. It will diverge like this. Okay, so a air bubble inside water is acting like a concave lens, not as a convex lens. But same a water drop outside somewhere in the air, that will act like a convex lens. Inside the air, this air bubble, or inside the water, the air bubble acts differently. Okay, so that's an important thing. Anyway, we got such a question. That's why we got a chance to explain that. Now, this is a little bit time-consuming thing. Okay, a fish in the water tank sees the outside world as it is. The fish is at the vertex of cone such that the circular base of the cone coincides. Okay, I'll explain like this. So the thing is, this fish is here. This fish, when it is looking, it will see the entire area like this. Why this is saying? Because of the lights bending like this, because the rarer medium to denser medium. So if it is going parallel like this, then what is the meaning? This angle is critical angle IC. If this is critical angle, this angle also should be, it's already marked here, critical angle. So based on that one, you have to solve. So you will get this equation. This is already solved equation they kept here. You can calculate like this. Okay, based on the, what you should remember is, see here, you have a level like this. Here, fish is here. So the fish is looking like this. So what happens is, the fish, the light will go like this. So that fish can see more area. Some more, if you go like this entire area fish can see. So what is the condition? This angle should be critical angle IC. If this is critical angle, here also critical angle, then using the remaining geometry you can see. So already they derived an equation for this R. This R is given by H by root of mu square. This one, by doing the triangle and all, we are getting it. No, by hurting this one directly by putting the values also you can do. Okay, we don't have time to go for this entire thing. Anyway, this material, this one will be shared with you, so you can do that one. Okay. So here another question is there. For the same value of angle of incidence, the angle of refraction in the three media ABC are 15 degree, 25 degree, and 35 degree respectively. In which media would the velocity of light be minimum? So here sin I by sin R is equal to refractive index. So from this one, otherwise you can do it like this only. It is coming like this, and it is bending more towards normal. So the angle is very less, means this will be having higher refractive index. This will have less refractive index, because when it bends more towards the normal, the refractive index is high. That's all. So different three media, it is going in three ways. Where it is bending more, that will have more refractive index. That's how you have to do it. Okay, the same thing with equation they explain. This is again same bulb question only, that previously we discussed about the fish. Instead of fish, it is bulb question. Okay. This is a concave lens of refractive index 1.5. Same thing, immersed in the water, that question. Okay, this same, both questions are immersed. You see here, it came for the board exam. Here, when it is behaved immersed, what happens? You see here, a concave lens of refractive index 1.5 is immersed in a medium of refractive index 1.65. What is the nature of the lens? Say 1.5 immersed in 1.65 means it will become the opposite one. That's what we discussed just now. A biconvex lens made up of transparent material of refractive index 1.25 is immersed in the water of same thing. Same concept is same only. See, under what condition does a biconvex lens of glass having certain refractive index acts as a plain glass? That is, when immersed in a liquid, that is, both should have the same refractive index. Just now we discussed. Then how does the focal length of a lens change when red light incident on it is replaced by violet light? That we discussed already. So the bending of the light, the red bends here, the violet will be bending more. So the violet will have lesser focal length, because if you take concave or convex, in both cases, the focal length will be different. Remember one thing, this is applicable for lens only. In the case of mirror, whatever be the color, it won't make any difference. Now the next one. Okay, with this one we'll stop, because this is an interesting thing. In the following diagram, an object O, that is this object here, where is object O? Here P is written. Actually, here it should be object. Okay, object O is placed 15 centimeter in front of a convex lens. That is, no, not here. This is O. 15 centimeter from here it is placed, and convex lens L1, for this L1, so focal length 20 centimeter, and the final image is formed at I. Here is the final image at a distance 80 centimeter. This is 80 centimeter from the second lens L2. Find the focal length of the lens L2. So how you can get it? The thing is, O is placed 15 centimeter convex lens L1 of focal length 20 centimeter. So what you have to do is, this is kept at 15 centimeter. Its focal length is 20 centimeter. So where the object is kept? The object is kept between the focus and pole. So what happens is, this is the situation is in such a way that you have lens here, and the focal length F is 20 centimeter. This is kept here. So what will happen? It will make a virtual image this side. So first you have to find out where the virtual image is formed. So its virtual image, you just put the lens formula, so you will get somewhere here. So this one you can calculate using the lens formula. Now already 20 centimeter here, and when you calculate this one, you will get that value also. Clear? So this value you will get. Now what happens for this lens? The object is here, that is 20 plus that value. Total value is the object, and this is the image. Object is there, image is here, you can find out the focal length. Okay, so let me see that whether it is done. Okay, the same way it is done. So they are getting this 40 centimeters. So the same calculation is same only. Okay, but I told the same step is there. So this type, we don't have time to do this one. So we will stop here. Our time is up now. Anyway, this remaining questions also is there. When we are sharing the materials with you, we will share these remaining questions also. In most of the questions, answer also is there. So for time being, we'll stop here. And actually tomorrow onwards, you will have a chemistry class. So we'll stop here. Thank you.